So, as I gave you a small brief introduction about myself, let's start with the first topic, which is simulation. What is simulation? Simulation is nothing but a numerical analysis technique which will solve your solve your problems or your models. It will analyze will your model will sustain under certain loading conditions and all. So a static simulation is a finite element analysis method used to determine the response of structure to constant or slowly applied loads. And as you know, our objective is to predict if design will fail or deform under the given loads and pressure. So for the simulation, for the static simulation specifically, there are three assumptions which we work on. First one is forces are always balanced. Uh, let's say you are applying a certain force, the another same amount of reaction force will act on the same body to neglect the force. Then second assumption is the material will behave like spring, because static simulation can only predict the model's deformation if it's elastic deformation. So the material behaves like spring. If you remove the load, it will go back to its original size. So we can only predict the way part will behave under loading in O2A region over here, as you can see. Sorry, as you can see, O2A region is used for static simulation. By the way, this is a stress strain graph. At From O2A, it's the certain part or any material will show you elastic behavior. After that, it will go on achieving its yield strength, and after it will again dip, and it will start its process of strain hardening, and after a certain point, it will start deforming plastically with and it will start nicking, and at a certain point, let's say point E, it will break or it will fail. So this is our stress strain diagram. Third, yeah, going back to the assumptions. Third assumption is no time dependency. Loads are uh, applied at very small piece. We ignore vibration, inertia, and impact forces in this simulation. So as I said, static simulation will reflect materials behavior from region O to A. This is known as elastic region. So we'll just skip all the basic engineering concepts. I hope you guys are aware what is strain, stress, and what is relation between them. Again, these are failure theories. We're gonna use a lot of failure theories for simulation. Mostly we use von Mises, maximum shear stress, and Rankine theory, which is maximum normal stress theory. Again, I won't go into all the failure theories. Let's start with the simulation and model setup part. So as you can see, this is my home screen of SolidWorks. I'll just open wherever my part is. Let's say it's in training static. So we'll start with a single part. I'll showcase every aspect of it, like how to set up the basic simulation study. Just let it load. Yeah. So this is a plate with a hole. It's a simple part, nothing complicated in it. So let's start with simulation. If you don't have your simulation add-in over here, all you have to do is go to options and drop down and add go to add-ins and just add SolidWorks simulation, and it will appear. Again, I'll if you have SolidWorks Premium license, you'll get simulation part. Otherwise, it won't be there. So let's start with the basic setup. First of all, we'll go to simulation tab, create a new study. After this, you'll get these types of study setup or different types of analysis. So we're gonna cover all these parts in this simulation webinar series. As this is introduction to SolidWorks simulation and static simulation, we only gonna look into static simulation, as it will be available for you in SolidWorks Premium and SolidWorks Simulation standard part. So let's start with this. Uh, First of all, I'll just give you a tour of SolidWorks Simulation interface. These are the parameters we're gonna define. Like let's say we have to apply material, we have to click here. This is for fixture advisor. Uh, from here we can add load or external forces, and this is for connection to give local interaction and component interaction. It is nothing but how it will behave when it will mate it's in assembly. So let's say there are multiple part, so with the help of this connections, we can we can set a boundary condition, and we'll give a definition how will it behave when it comes within contact with another part. So let's start with basics. All First of all, we have to apply a material to the part. It's a basic step. So I will just click. We'll just right click on here and apply or edit material, or we can go from here. We just have to click it. For now, we'll keep it as alloy steel. All you have to do is click apply, and it will apply itself. Since this is a single part, there are no multiple parts over here. We don't need to add any connections over here. So moving on to the next, it's fixtures. So there are multiple types of fixtures. So let me showcase all of them for you. First is called fixed geometry. So you can see example over here. So it will constrain all the degrees of freedom of the part or face or edge or any entity we are selecting. So it won't move, it won't rotate or translate in any direction in any degree of freedom. Upon next we have roller and slider. So the translation degrees and rotational degrees of freedom will be a constraint, and we can only slide it as shown over here. Next, we have fixed hinges. Mostly we give this fixture when are we bolting something or there's a hinge in a part. Moving on next, we have advanced fixtures. We will see these fixtures in next webinar series, next webinar of the series. So for now, I'll just select a fixed geometry and I'll select this face. Now I'm gonna apply load on this face and I'm gonna stretch this part. So I just wanna check what is the maximum deflection, or how will it act if I put, let's say, 500 newtons of force over here. So for that, I'll just go to external loads. Again, There are multiple types of loads over here. We can add force, we can add torque, pressure, gravity, centrifugal forces, and everything else. So let's start with force. I'll slowly will showcase all these things with you, and let's start. Uh, so all you have to do is put the force how much force you wanna apply on that piece. Let's say I'm applying 500 newtons of this force, but I don't want to put force in this direction. I want to stretch the part, not I don't want to compress it. So I'll just click over here and reverse its direction. So it will just reverse its direction. Upon here, non-uniform distribution. Let's say you are simulating a pressure. Let's say there's a tank, and you have to check the pressure. You have to simulate will the tank will hold the. Let's say we are filling that tank with water, and you have to simulate will that tank will be able to hold that water or not. So for that, we have to use non-uniform distribution for that. Uh, since the pressure at the top of the surface, or let's say top of the tank, will zero, and as we go downwards, it will increase. So for that, we have to use non-uniform distribution. And if your force or pressure is uniform, you don't have to use this tab. So for now, I'll just skip this part, and yeah, we're gonna look into this part after some time. So after this, I'll just add a load. I've given direction to it. After this, there's one more important part called meshing. So when we create a mesh, you can see there are multiple options are here. As as you can see here, there's a there's an option to control the mesh size, whether it will be fine or coarse. Uh, if we go to fine, the element size will decrease and number of element will increase. It will give you more accurate result, but it will take a lot. It will take more time to simulate. So we mostly we mostly keep this as the whatever SolidWorks software thinks it will be appropriate. Yes, we let's say there's a we will get more into the meshing in second chapter. So I'll just give a brief idea what is this. Standard mesh, it will create a standard mesh on the part. It the aspect ratio will be much more harder to, or it will be it won't be accurate if there's a curvature in the part. So since this is there's a curvature or there's a hole in this plate, we won't use standard curvature. We'll stick to curvature based mesh or blended curvature. Let's say there are multiple curvature in the model. So when I if there are multiple curvature, we always go for blended curvature. And when there's a normal hole or anything else which is a singular entity, we can go with curvature based mesh. So for now, we're gonna use curvature based mesh. After this, we can also set mesh quality of the part. For now, we'll keep it its draft. So draft will create a, as specifies, high high will create a high quality mesh, and draft will create a draft quality mesh. Since this part is pretty much simple, it will there will not be much more of difference in the results. So keep this as a draft, and a draft size mesh will take much more less time to simulate and give us the answers. So we'll keep this as draft and we'll click on OK. Now you can see the our mesh has been generated. So if you want to, uh, yeah, sorry about that. Yeah, after this, we'll just click on run this study to simulate this part. Yeah, so this will give us the result. As you can see, the von Mises stress will just change the results to MPa. So, yeah, for that, you have to just have right click on the plot or results, go to edit definition, and you can change your units from here. We're gonna keep it as megapascal, and let's say in your company or in your organization you are not referring one Mises as failure criterion. Uh, you are you're going with a normal stress or any other any other failure theories. For that, you can choose all your failure theories from here. For now, we're gonna stick with von Mises. So deform shift is nothing but, since we applied 500 Newton, it should not be it should not deform this much. So this is a deform shift, and we have exaggerated the deformation of this. So we'll just keep it as true scale. So it will give us the true shape of the part. After that, we'll just click on OK. So this is our true shape. Yeah. And from plot, you can see our maximum von Mises stress is 1000 1.43 megapascal. And also you can see over here the yield strength of material also been showcased. It is around 620 MPa. And let's say you want to check the stress on a particular point. All you have to do is right click on stress, go to probe tool, and just select on node or location where you want to check. So here at a node 1562, the value of stress is 1.35 MPa. And let's say you want to select a surface or any entity. All you have to do is go to on selected entities, click on the face, and click on update. So it will give you the average stress on this face, maximum and minimum stress on this face. So other than that, we can also see the displacement over here. Again, the maximum displacement is it's very less. It's around 0.0005 mm. Uh, and then you can also check your strain from here. And let's say you want to add another plot or another. All you have to do is go to the results tab, right click on it, and add a plot of whatever you want. Let's say you want to add a plot of factor safety. All you have to do is hover over here, click on it, and just, yeah, and there you are. And this is your factor of safety plot. So you can see uh, it's safe or not. It's up to according to your standards. Again, let's say you want to calculate the reaction forces acting on this on this face. Since we have applied 500 Newton, it should be 500 Newton because it's a simple problem. But as we go into details and assemblies come into the picture, we we are we usually get stuck for finding reaction forces. So we have that covered for you as well. All you have to do is go to results, right click and go to list result forces. After that, for reaction forces, all you have to do is select the face where face or entity where you have to check the reaction forces. Again, update it, and it will showcase all the reaction forces over here. As you can see, we have applied a load in x direction, which is 500 Newton. You can see over here, and these are the negligible values. It will also give you those, and resultant will be 500 Newton. So this was for part. Let's say there is another part, but stress concentration is on edge, and I want to calculate proper proper stress on that edge or on that part. So what can I do? So we can do a mesh conversion study to check the perfect mesh for it, or we can use mesh control to refine our results. For that, I'll show you another example. So let's say this is my L bracket. I'm fixing it in this phase, or this phase. We'll keep it. We'll fix it in this phase, and we will apply the load on this phase in parallel direction to the same phase, and we have to determine the as we can assume, or we can just as we can assume this stress concentration will be on this fillet. So we want accurate results over here. So we need to refine mesh over here. So we can use mesh control. So all you have to do is again set up the study as usual, apply the material. Since there's no one, this it is a single part, there's no need to add connections. We'll go to fixtures, we'll click on this part, we'll select OK. For this external loads, we'll click on force. We're gonna apply force on this face, but it won't be uh, any axial force. We're gonna use shear force over here. So to change its direction, all you have to do is select the selected direction and give it a reference geometry. For this, I'm going to select this edge. So you can see arrows, upward arrows. So it will apply force vertically on this face. So we'll just change its changes in direction. It will, yeah, and we'll keep the force as again 500 Newton. We don't want it to fail. So yeah, we'll keep it 500 Newton. Yeah, now coming to the mesh control part, all you have to do is right click on it, apply mesh control. For that, you can select either edge, face, or the vertices or any other entity. So for this, I'm gonna use this face, and I'm gonna increase the mesh density and increase it to fine, or we can change it from over here also. So I'll keep the So this is nothing but element size. This is the maximum element size, and this is the minimum element size. So maximum element size over here will be around 1.2 and minimum will be around 1 mm. So we'll after this we'll just click on OK, and again we'll go to create mesh. We are gonna keep this as blended curvature. You can see calculate option here to calculate minimum element size. It will only pop up when there's a when blended curvature best mesh is selected. Otherwise, it won't appear. So for this, we'll calculate this minimum element size. All you have to do is select curvature or minimum element size from mesh control. So we'll select on minimum radius. Usually we do this before applying mesh control. All you have to do is calculate it, and it's giving us the minimum element size. It is around 1.9 mm. So we'll just click on apply. So it will reflect the minimum element size over here. After this, we'll just create the mesh. Remember that we are not changing the mesh control. So element size over here will be what minimum element size will be 1 over here. So we'll just click on OK. So it will give you a mesh like this. So you can see the mesh is more fine over here rather than other parts of the body. So in this mesh, there's another option called element size growth ratio. So what it does is, let's say there's a element of 1 mm over here. So next element over here will be around 1.4, means it will multiply by 1.4, and it will give you the size of the next or adjacent element. So in this way it will increase the element size. It won't directly increase it from 1.9 to 4.8. It will give us inaccurate results or some problem in solving our geometry. So again, we'll click on OK. It will create the mesh, and we can run this study. So see, you can easily control your mesh setting, and you can see the where the stress is concentrated. Moving on to next, we'll to showcase you all the connections. I'll just open a assembly. For this, I'll again static. Yeah, yeah. Just let me hide these planes. Yeah. Uh, you can see a plier assembly over here, and there's a piece of metal which is clamped by the pliers. So we want to check whether, like, what force, or after applying a certain force, how will it behave, where will be the stress concentration, and what design change should we imply or should be made. So let's move on to the simulation. uh, After creating static study, we can see multiple parts over here. This is arm 1, arm 2, This is flat, and this flat is metal piece, and this is pin. So first of all, we'll just apply material to all. If you want to apply material to each and every part, let's say your arm material is alloy steel, and your metal piece is of carbon, plain carbon steel. So you can apply it differently. Like you can apply different material for a different part. That's possible also. So, and for the pin, we'll keep it alloy steel again. Yeah. So there are two ways to simulate this. Since we're gonna apply force over here, we can do one thing. We can keep this metal plate over here and give fixtures to this plate, or we can remove this metal plate and we give fixtures to the other part, like these two faces. So first of all, we'll keep the flat and like material piece over here, and we're gonna apply the fixtures to it, and then and in second study I'll show you how to exclude that part. For this, we're going to use again fixed geometry. For this, you don't need to select all the faces. You can select a single face. I'm just selecting it. Okay, let's select only single face. I don't know why I'm selecting that. Yeah, let's go. After this, we're gonna put external loads. Yeah. So what I've done is I've created a separate surface on this plier. So I can easily apply the force on only this part. So for this, I'm selecting these two faces. Again, I'm gonna keep my force as 100 newtons. So I'm gonna select it for it. Yeah, I kept the direction of the force as normal. No need to add selected direction. No need to add any other reference geometry. So we'll just click on OK. Yeah. Another part, before meshing, you have to give all connections, all component interactions, and whatnot. After that, after setting up all the all the parameters, only after that go for meshing. Don't start. Let's say you have applied the material and you have done the meshing, and after that you're fixing the part and adding connections. So after that process, you have to again remesh the part. So keep the meshing part uh, just before running the simulation. So what is component interaction? So component interaction will assign a global interaction between all the parts. So there are three types of global interaction. First one is bonded, second one is contact, and third one is free. I'll just show you what are those.